Greetings and welcome to the recitation video for problem set number 2 of Chemistry 221, and I'm really glad to have you here. This problem set will focus on Chapter 2. Chapter 2 is a little bit more interesting than Chapter 1 because we get into some actual chemistry, which is kind of cool. Just as a quick reminder, before you turn in the problem set, there's a couple of things I really want to see. First of all, show your work. All right, we're getting into problems which are more involved, and I want to see how you set them up. I want to see your calculations, the numbers you use, stuff like that. Don't turn in just the answers. That's not going to be worth as much. And then while you're watching this video, you do not have to watch it from start to finish. You can scrub through it. You can move the little slider back and forth. You can speed me up to 1.25 or 1.5 speed, whatever works for you, and watch it that way, which is fantastic. And while you're watching this video, I want you to self-correct your problem set. So in the lower right-hand corner right there, you can see that this person, when they did their problem set, they got question 3 right. They put some kind of symbol next to it so that I know that they know that the problem is right, and that's great. On the other hand, they missed problems 4 and 5 a little bit. They put down then some correct marks to show how they would get it right the next time, and that's fantastic. So mark every problem. Mark the ones you got right as well as the ones you got wrong. And if you miss it, then just self-correct. And again, it's totally fine to miss problems here as long as you self-correct. I've had students literally miss like every problem when they turned in a problem set, but they self-corrected everything, full credit. On the other hand, I've had students that got every problem right. They did wonderful work, but they didn't self-correct their work. They didn't get as many points. So show lots of self-correct work. Definitely very important. You should use a periodic table on this problem set. mhchem.org/per-tab is the one I want you to use, and that's the one you'll be able to use on quizzes and exams. So check it out. And if you have questions on any of this material, please reach out to me. You can also talk to the AVID/LSC Center located above the library. Their website is listed right there, and they can help you out as well. Okay, without further ado, let's get into this problem set and see what it has to offer. The symbolism used in the top part right here is very common for isotopes, and let's talk about what the symbol means. Now, the lower left corner, Z, that's the atomic number, and that's the number of protons, and that number comes from the periodic table. Now, the X, which is associated with the Z, that's the symbol on the periodic table. So, for example, number 4 is beryllium, so you would write a 4 for the lower left and a BE for the symbol X. So X can be one letter or one letter with a second letter, like in beryllium. Either one is fine. The top thing there, that A, that's the mass number, and that's equal to protons plus neutrons. So for this first one here, we have fluorine with 10 neutrons, and fluorine is number 9 on the periodic table. So 9 is going to be Z. The symbol for fluorine is F, and the mass number, which is A, the upper left thing, 9 plus 10, it's going to be 19. So you would write this particular isotope, which we'll talk about in a little bit more, you would write it with a 19 in the top, a 9 in the bottom, and a big F for the symbol. Fluorine, again, is not Fl, that's fluorovium. That's a new element and quite different than fluorine. Fluorine is just F. The second one, chromium. Chromium is number 24. The symbol for chromium is Cr. So we'd have 24 in the lower left, Cr for the symbol, and then 28 plus 24, or 52, would be the mass number. So that's how you would write that particular isotope. And then finally, the last one, xenon. Xenon is Xe, and the atomic number on the periodic table is 54. So you'd have 54 in the lower left. The symbol would be Xe, and in the upper left corner, the mass number, you'd have 54 plus 78, 132. Copper exists as 2 isotopes, copper 63, and that number right there, 62.9298, that's the exact mass in AMU of that isotope. Most of the masses are a little less than what the mass number is, so you can see that 62.9, if you round it up, would be 63. We'll talk more about why that is in Chem 222. The little u is a symbol for atomic mass units, or Daltons, all right? So it's a very, very small amount. But anyway, copper has 2 isotopes, copper 63 and copper 65, and it says, what's the approximate percentage of copper 65 in different samples of the element, and there are 5 possibilities. Well, for this question, you must know the atomic mass of copper, and that comes again from the periodic table. So with my periodic table that I'm using, if I look up copper, which is number 29 on the periodic table, the answer is 63.546. So that means that the average mass of a copper atom, 63.546. Now, we're trying to figure out the abundance of copper 65, and copper 63 is closer to 63.546 on the number line than copper 65 is. So one way to think about this is that copper 63 must be a pretty high percentage, because copper 63 is closer to that 63.546. So the abundance of copper 65 will definitely be less than 50%. So let's think for a minute what the mass would be, the average mass of copper, if you had 50% copper 63 and 50% copper 65. And if you think about it, if you had 50-50, the average mass, the atomic mass, would be about 64. But 63.546 is quite a bit less than 64, 50%. And as you get closer to 63, that means you have more of the copper 63 and less of the copper 65. So right away, we can pull out C and D and E. And the question is about 10% or 30% copper 65. And I would argue, in a hand-waving kind of explanation, that probably answer B is the best answer. Because with B, the average mass, 63.5, it's not 63 or 63.1. There is obviously a pretty good amount of 65 to pull that average closer to 63.5 than 63. So I would think that the best answer here would be B. Now, if you don't like this way of doing it, there is another way to do these kind of problems. And I'm going to show you how this works on the next question. But the answer for this one is about 30%. And again, if you use the almighty Google, you'll find that copper 65 is about 30.83%. So that's pretty close to the 30% number. Copper 63 is roughly 69.17%. So quite a bit more 63, and that makes sense because of the 63.546. This is one way that you can kind of see what's happening here. And on the next question, we'll look at another method that you could use on question number 4. And I'll talk about that in question number 5. Antimony has 2 stable isotopes, antimony 121 and antimony 123, and there are the exact masses. And again, if you look at the first one, 120.9, that's pretty close to 121, and the second one, 122.9, is pretty close to 123. And it says calculate the percent abundance of these isotopes of antimony. And again, that little U there is the atomic mass unit, sometimes called Dalton, just a really small amount of grams. Now, for a problem like this, you have 2 isotopes and you have 2 masses, and we need to find what the percent abundances of these isotopes of antimony are. Now, for a question like this, similar to what we did on number 4, you're going to need to have the atomic mass of antimony, and antimony is number 51 on the periodic table. Before we do that even though, there are only 2 isotopes. And if there's only 2 isotopes and you added them together, they would equal 100%. So if you had something, say that at an event that was 60% female, and then we were only cisgenders here, by the way, and stuff. Sorry, I should be careful of these things these days. Anyway, if they were all just cis males and cis females, then we had 60% cis females, then you'd have 100 minus 60 or 40% cis males. All right, if there's only 2 things, adding them up together equals 100%. Now in the decimal world, which is what people will use with these kind kind of things, instead of percentages, they'll write them in a decimal version. So 1 is the decimal version of 100. It's like 100 divided by 100, or 1. So x plus y equals 1 just says that the abundance of the antimony 121 and the abundance of the 123 equals 100%, or 1. So in this problem, x is going to represent the mass, the abundance of antimony 121. And we're going to see here that 1 minus x represents the abundance of antimony 123. And where that 1 minus x things comes from is that both of the antimony isotopes together equals 100%, or 1. So the abundance of the second isotope is just going to equal 1 minus x. Okay, so remembering that then, and also looking on the periodic table and seeing that antimony is number 51 is about 121.76 or so, you can set up something that looks like this. So let's break this down. 121.760 is the atomic mass on the periodic table for antimony. It's the value that I see with my periodic table. And that equals the abundance of the first isotope times its mass, plus the abundance of the second isotope times its mass. So this x is the antimony 121 abundance, a decimal version, and we're going to multiply it by its mass, the 120.9038. And then normally we'd have plus y times the other one, where y is the other isotope. But up here you can see that y equals 1 minus x, and that's what we're going to do in this problem. Instead of using y, we'll use 1 minus x. If we used y there, we'd have an x and a y, two equations, one unknown. Those kind of equations are pretty difficult to do. So in this case, if you substitute in for y 1 minus x, then you have one equation and one unknown x. So that's how this is set up. Now, the math here isn't too bad. We'll multiply x by 120.9038 to get this term. And then we use what's called the distributive property. You start off by going 1 times 122.9042, and that's this thing right here. But then you also go minus x times that. So you have minus 122.9042x. So now you can see by this equation, you've got a number, and this is a number, 122.9042, and then you also have here two things with x. So you want to combine the x terms, and you want to subtract 122.9042 from both sides. That'll get the 122.9042 out of the right side, and it will combine the numbers on the left. So if you do that, 121.760 minus 122.9042, that's where this number, this minus 1.1442 number came from. And if you take 120.9038x and you subtract 122.9042x from it, you get negative 2.0004x. So notice what we did there. We got the x's on one side, we got the numbers on the other side. And what you want to do here is you want to divide both sides by negative 2.004. And that's going to give you the x's, x on one side, and you'll have a number on the other side. And lo and behold, 0.5720 is the abundance that pops up. And that number, if you multiply by 100%, means that antimony 121, 57.20%. And that's kind of cool. On the other hand, the antimony 123, you go 1 minus 0.5720. That's what we did up here. And that's going to give you 0.4280. That translates to 42.80%. That's the percentage of antimony antimony 123. Notice that the 121.760 number stops at the thousandths, this number right there. And what that means when you subtract 122.9042, you can really only count the first 4 sig figs. And that's why this number is a 4 sig fig number. It shouldn't be 5. If you look at just the division part, when you divide by negative 2.004, it looks like it should be 5. But because of that subtraction, you can only use 4 sigs, and that's what's going on there. Couple of things. Both of the abundances together should equal 100% or 1 if you're using the decimal version. And then finally, you can kind of use these numbers and see if it makes sense based on the average. Now, 121.760 is closer to 121 than it is 123. And because it's closer to 121, the abundance of the antimony 121 should be greater than the antimony 123 abundance. And that's what we see, all right? And that's good. 121.7 is closer to 121 than it is 123. That's why the antimony 121 abundance should be higher. So that's a nice way to check yourself with this kind of problem. Now, you can do this exact type of problem on question number 4 with the copper. If you didn't like my hand waving thing that said it was 30% copper 65, I completely understand. Instead of, at this level right here, instead of 121.760, you would have that 63.546 number, and that would equal X times the copper 63 abundance plus 1 minus X times the copper 65 number, whatever that was. And you'd go through these problems and you'd find those percentages for yourself. And that is honestly probably a better way than my hand waving. So this process is important. It only works if you have 2 isotopes. If you have 3 or more, you have to use other techniques. But it is a powerful tool, and it makes sure you've got the skills to pay the bills that are coming up with the kind of problems we're going to do. Here are the symbols for 5 of the 7 elements, or at least the 7 I could find, whose names begin with the letter B. And those are B, BA, BK, BI, and BR. Match each symbol with one of the descriptions below. And first one says a radioactive element. Okay, if you have a periodic table which lists the states of matter, all right, you might see a lot of the elements are black because they're solids, red ones are usually gases, blue is liquids, but there's also a lot of clear elements. And if you see an element with just like the outline, a lot of times that's one way to tell that it's a radioactive element. But in the periodic table that I'm recommending you use at mhchem.org/per-tab, we don't have that, all right, which is too bad. All these symbols are solid. So another way to answer A is that basically everything past uranium is considered radioactive. Some people say it's even before that. Some people say it's lead. Some people say it's uranium. All I know is that there's going to be a lot of them which are that way. And either way you do it, either lead or uranium, or even some people use bismuth, Bi, but whatever, berkelium, Bk, is one that's past that. And berkelium is a radioactive element. It's really radioactive, actually. And if you look up online and stuff, you'll see that berkelium is quite an exciting element. It does some interesting things. But either way, berkelium here is the radioactive one. If you really have to guess, all right, usually the most radioactive is the biggest one. And that's not all the time the case, but a lot of times it is. B, a liquid at room temperature. All right, there are only 2 liquids on all the periodic table at room temperature, and one of them is mercury, and the other one, if you didn't know, it's quite all right, is bromine. Bromine is actually kind of a noxious looking brown liquid, pretty nasty stuff, but it is a liquid. So at room temperature, only mercury, Hg, and bromine, Br, are liquids. And again, if you didn't know it, it's okay. okay. The periodic tables that we would use in the classroom show the states of matter, which are really nice. But if you didn't know it, it's okay. C, a metalloid. A metalloid is one of the elements that kind of is on both sides a little bit of the metal line and the non-metal line. It's things and stuff that could be a non-metal and it could be a metal. It's hard to say. Metalloids sometimes behave like metals. They'll give up electrons, be positive, stuff like that. Sometimes, though, they act like non-metals and they'll make covalent bonds with other non-metals. It's a really interesting kind of thing. There isn't, in my opinion, a real hard and fast metalloid definition. However, usually the metalloid line starts at boron, and boron is the metalloid of this group. Boron does act like a metal sometimes, and sometimes it acts like a non-metal. It's very hard to say. It's a true metalloid, and in this class, we'll use boron in both its metallic capacity and as a non-metal, so basically acting like a metalloid. Now, alkaline earth elements are elements in group 2A or group 2 on the periodic table. And that starts at Be, another another B element, beryllium, but beryllium's not in this list. But if you keep going down, Mg, Ca, Sr, finally you get down to Ba, barium. And barium is an alkaline earth element. So all the alkaline earth elements, again, are group 2A, alkali metals are group 1A, etc., etc. And then finally, a group 5A element. Here we're using the quote-unquote American version of the periodic table, where there's A's on the far left, 1A and 2A, and on the far right side, starting with boron and aluminum, that's group 3A. Then you go 4A, 5A, etc., etc. So 5A is also the nitrogen group. So you essentially want to start at nitrogen and just work your way down. And if you do get down there, you get down to bismuth, Bi. So this is just one way to kind of have some fun with the periodic table. Again, if you weren't clear on the radioactive or the liquid, it's not a big deal because depending on how this class is being taught, this could be easier or harder. But hopefully you can at least see that the metalloid was boron, alkaline earth, group 2A, barium, group 5A, bismuth, etc. As an aside, as of right now, there are no J's or Q's on the periodic table for permanent symbols for elements. So if you ever get an element that you get to name, add a JQ or something like that to it, and I will be very happy. Doesn't take much to keep me happy, obviously. In this question, we're going to see how an empirical formula can be derived from a molecular formula. And the punchline here is that empirical formulas are the smallest whole number ratio of atoms in a molecular formula. So in the first one, C6H6, focus on the numbers, all right? If you can divide those numbers and make them smaller, and whole number smaller, by the way, that's going to be an empirical formula. So if you divide 6 and 6 by 6, then you get C1H1 or just CH. That would be the empirical formula of this compound. All right, so it's pretty chill. The next one, C8H4O8, if you divide all of those by 4, you'll end up with whole numbers. So for example, 8 divided by 4 is 2, and 4 divided by 4 is 1. So the empirical formula here then would be C2H02. If you divide all of those numbers by 4, those are the numbers that are left over. And again, you want whole numbers. That's going to be really important too. H2O2, if you divide both of those 2's by 2, you get the empirical formula of HO. But the next one, I'm kind of throwing a little bit of a monkey wrench at you. 2 and 1, the 2 by the N and the invisible 1 by the O. Well, you can't divide those numbers by another number to get a smaller whole number ratio. So for example, you could divide those numbers by 2 and get N10.5, but whole numbers are really important in chemistry. So this molecule actually has the same empirical formula as it has molecular formula. N2O is the smallest whole number ratio of atoms for the molecular formula. So this molecule has the same empirical formula as molecular formula. You will see that once in a while in molecules, for example, like water, H2O. You can't make that molecule structure any smaller with and still have whole numbers. Whole numbers are pretty important when it comes to empirical formulas. In this question, I want you to calculate the molar mass of these compounds. Now, the molar mass is going to be so important to us in future chapters, and the molar mass is the grams of that compound in a mole of the compound. And if you have a mole of the compound, you have 6.022 times 10 to the 23rd molecules, stuff like that. So what you want to do on this problem is, first of all, make sure you have access to a periodic table. And again, I want you to use the periodic table located at mhchem.org/per tab. This is the one that you'll be using on quizzes and exams, and the more familiar you are with it, the better. So for example, on CH4 then, you would look up carbon, which is number 6 on the periodic table, and hydrogen, which is number 1 on the periodic table. And if you find out those numbers to the hundredths place, 0.01 grams per mole, you want to add them up. So carbon is 12.01 grams per mole, hydrogen to the hundredth, 1.01 grams per mole. Carbon, there's one of them, so carbon would be 12.01. Hydrogen, there's 4 of them, so you'd go 4 times 1.01, and you add that up together to give the overall molar mass. If you got 16.05 for your answer, pat yourself on the back. Woohoo! You are good to go. So again, to the hundredths place, which is usually all you need, that would be 12.01 for carbon. Hydrogen to the hundredths, 1.01. Multiply that by 4, since there's 4 hydrogens, 16.05 grams per mole. Water is H2O. We're going to use this a lot. It's a good number to know because we're going to be seeing it a lot. So again, hydrogen, 1.01 grams per mole from the last one, and there's 2 of them, so we'll multiply that by 2. So oxygen to the hundredth is exactly 16.00. So add 16.00 plus 2 times 1.01, 18.02 grams per mole is the molar mass of water, and we'll use that quite a bit, so just kind of get ready. The last one is an example of an organic acid. We'll talk more about that in a later chapter, but again, the process here is similar. You need to look up carbon, hydrogen, and oxygen. So carbon is still 12.01, and there's 2 of them, so times 2. Hydrogen is still 1.01, multiply it by 4, and oxygen, 16.00, multiply it by 2. Add all of those numbers up, 60.06 grams per mole would be the molar mass of this compound. So this is how you do it manually, and I totally encourage you to make sure that you know how this process works. That being said, it can be really useful to find a molar mass calculator, and molar mass calculators can be found on the web as websites. You can also have apps on your smartphones and computers that will do this for you, and I use one very regularly. So when you have a really long formula, instead of having to do this manually, you can just put the formula in and hit enter, and it gives you the molar mass, which is pretty cool. So that can be really helpful, but you can also do it manually like this problem represents. It's totally up to you. Let's calculate the mass in grams of all of these different mole amounts. Okay, so we just went through talking about the atomic mass numbers for antimony and copper, and those numbers at the time we were using in terms of atomic mass units, AMUs. But the real use, in my opinion, of those numbers isn't as atomic mass units for an average atom. All of those numbers also mean number of grams in a mole. So that's really cool. So let's look at the first one here for gold. Now gold is number 79 on the periodic table. Its symbol is capital AU, AU. And you can see that by gold, there's a number 196.967 is what my periodic table says. And that 196 number is literally grams per mole. So if you have 4.24 moles of gold and you want to see how many grams that is, you would just multiply it by that number. Let's talk about sig figs. On my periodic table, the number I just quoted you, 196.967, this person did not use all of those sig figs. And honestly, that's okay. We have 3 sig figs going in. 4.24 is 3 sigs. The important thing is just to have 3 sig figs out. So you can use 197.0, that's fantastic. You could also use the number I quoted earlier, 196.967. You just don't want the sig figs to be cut down by the molar mass. So it gives you, as the chemist, some flexibility in the numbers you use. You wouldn't want to use like only 2 sig figs for the molar mass, because that would cut your sig figs down to 2. So using 4 sig figs, 197.0 is fantastic. Regardless, in the calculator, I had 835.28. The way I did it, I rounded up to 3 sig figs. That means I'm cutting it off after the 3 sig fig, after the 5. 2 is between 0 and 4, so I don't do anything. 835 grams of gold. Cool. Helium, number 2 on the periodic table. Helium has the symbol He. And if you look at the number for helium, it's about 4.003, depends on your periodic table. So that's the grams per mole of helium. And 15.6 moles of helium means you want an answer of 3 sig figs. So in this problem, I did use 4.003 grams per mole. I multiplied it by the 15.6. You can see that the moles of what you started with cancel the moles in the bottom. You've got just grams of helium, 62.4 grams of helium. The next one, 0.063 moles of platinum. Platinum is PT, number 78 on the periodic table. Platinum has a molar mass of 195.085. So if you take the moles and you multiply it by that number, you're going to get an answer. But how many sig figs should we use on this question? The last 2 problems were 3 sig figs. 4.24 was 3, 15.6 was 3. But remember, the zeros that start a number usually don't count in terms of significant figures. So 0.063 is a 2 sig fig number. So that means the answer is also going to be just 2 significant figures. So I used 195 grams per mole of platinum. I multiplied it by 0.063, 12 grams of platinum. And again, if you wish to use the complete version of platinum, I have it as 195.085. That's fine. I don't think you're going to see it's going to make a difference. This number right here might change a little bit, but the final answer shouldn't change, and that's kind of cool. And then finally, same thing, last one, we have a scientific notation, moles. That's okay. Multiply it by the molar mass of plutonium, which is Pu. Plutonium, 244.06 grams per mole. Multiply it by 3.63 times 10 to the minus 4. I had 0.0886 grams of plutonium. Notice on that one, the first, cut it off after 3 sig figs. That means after the 5. The first digit is between 5 and 9, so I rounded 0.0885 to 0.0886. We're starting with grams, and now we want to go to moles. So we're going to use those numbers on the periodic table once more. And again, the punchline, like we saw, is make sure your sig figs keep going forward. So sodium is number 11 on the periodic table. You can look at number 11 for the molar mass. 16.0 is 3 sig figs, so I used 22.99 there. That came out to be 0.696 moles of sodium, moles of Na. And again, round up, that 5 is the third sig fig, 9 is the first digit to be dropped, so you want to make the 5 a 6.696 moles. Tin, Sn, in the same group as carbon, so grams divided by the molar mass of tin, which is about 118.7 grams per mole. I had 7.38 times 10 to the minus 3. Yes, you could write 0.00738, and that would be fine. But do not make your instructor count your zeros. If you have more than 2 zeros, you run into real possibility that I'll just get a little bummed out at you, okay? So use scientific notation if there's a question, all right? 10 to the minus 3, 10 to the positive 3, those are when you should start using, I think, scientific notation. If I have to count your zeros, I will not be pleased. And because I grade your assignment, assignments, all right, this is probably something to pay attention to. Just don't make me count zeros, all right? I have better things to do with my time, and you do too. And if you know how on your calculator to go between regular mode and scientific notation mode, that's not going to be a problem at all. So again, a reminder, that's something you should check out. Know on your calculator how to go from one format to the other. The next one, 0.0034 grams of platinum, we'll divide it, by the molar mass. Notice here how we cut this number down to 2 sig figs. 0.0034 is a 2 sig fig number. You could write that 3.4 times 10 to the minus 3 if you'd like. Divide it by at least 195 grams per mole, 1.7 times 10 to the minus 5 moles of platinum. And then finally, there's grams of xenon. So we'll divide the grams of xenon by the molar mass of xenon, which is number 54 on the periodic table. And if you do that, xenon's about 131.3 grams per mole. That comes out to be 7.49 times 10 to the minus 3 moles. Cool. The recommended daily allowance, or RDA, in the United States of iron in your diet is 15 milligrams. So what that says is that every day, the average human being in the United States, they recommend that you have 15 milligrams of iron as intake. That number oscillates. If you're a pregnant woman, it's more, and children, it's different, and stuff like that. So, but for the average person, 15 milligrams. Now, on a mass balance scale, you can weigh 15 milligrams out, and it is really small. It would easily fit on your pinky. All right, it's a very, very small amount. So what we're going to do in this problem is we're first going to figure out how many moles we have in 15 milligrams, and then we're also going to figure out how many atoms are in the 15 milligrams. Okay, so what we're going to need to get to moles here is we're going to need the molar mass of iron. And iron is number 26 on the periodic table. It's like 55.845 grams per mole. But 15 milligrams is not grams. So you first need to convert milligrams to grams. There are 10 to the minus 3 grams per milligram. So you could go 15 times 10 to the minus 3, or you could take 15 divided by 1,000. That's another way to do it. But you've got to turn milligrams to grams and then grams per mole. So the first part of this calculation, we're just going to turn milligrams to grams, and you can see that we do that because milligrams on the top cancels milligrams on the bottom, and you've got grams left over. And that's good because the molar mass for iron, 55.85 or so grams per mole, you can see the grams on the top here cancels grams on the bottom. The only unit left standing, if you will, is moles of iron. So the 15 milligrams is 2.7 times 10 to the minus 4 moles of iron. Whoopie-doo. I don't know, as a PhD chemist, what 2.7 times 10 to the minus 4 moles really means. All right, doesn't really equate very well. The moles are good units for figuring out how molecules are made, but conceptually, it's kind of strange. So this part right here is like, oh yeah, whatever. But the next part, I promise, is kind of cool. We're going to figure out the atoms of iron. And once you have moles, this is an easy thing to do. If you need atoms, that's when you need Avogadro's number, 6.022 times 10 to the 23rd. And that number represents the number of atoms in a mole. So if you take 2.7 times 10 to the minus 4 and multiply it by Avogadro's number, all right, 6.02 times 10 to the 23rd, whatever, just make sure you've got at least 2 sig figs to do it. The answer comes out to be 1.6 times 10 to the 20th atoms of iron. And in the calculator, it's this number, but 2 sig figs are cutting it off, etc., etc. The E20, by the way, is the calculator's way a lot of times of writing times 10 to the 20th, and you're welcome to use that as well, or instead of the formal times 10 to the 23rd, etc. However, I want to step back for a second with you, and let's think about the magnitude of that number. In powers of 10, all right, 10 to the 3rd is 1,000, 10 to the 6th is 1,000,000, 10 to the 9th is 1 billion. So 2 10 to the 9ths or 10 to the 18th would be a billion billion. And you have more than a billion atoms of iron in your 15 milligrams. And remember earlier, I said your 15 milligrams, it can literally rest on your pinky. It's a super small amount. And like if this was something you had to do like a vitamin, I mean, you just lick your pinky, the 15 milligrams would be in you and you wouldn't think twice about it. But what I want to bring up to you is the number of atoms that we as human beings consume every day. 15 milligrams is just the amount of iron you're supposed to have. It doesn't say anything about the amount of protein or the amount of sugars and fats and carbohydrates and all those kind of things. It doesn't say anything about that. This is just the iron, and that is a lot of atoms. So if you go to the store and you have a sandwich or you drink a cup of coffee or something like that, you are just consuming an incredible number of atoms. And that's something that as human beings, we have just adjusted to amazingly well. We would not be able to count in our lifetime, I would argue, a billion atoms of anything. And that's more, like I said, than a billion atoms. So we're going to start seeing how these numbers of atoms are really incredible. And it's something we do every day. We just don't think about it because they're so small and stuff. But I'm trying to enlighten you. Oh, chemistry. In an experiment, you need 0.125 moles of sodium metal. And sodium is actually a pretty soft metal that you can cut with a dry knife. Dry, we'll talk about why that's important later, but trust me, you want the knife to be dry. So let's say in this problem, we have like an experiment and we need 0.125 moles. And for whatever reason, we want to make a block of sodium, a cube of sodium, okay? And the question is, what should the volume of the block be in cubic centimeters? And if it is a perfect cube, what's going to be the length of the edge of a cube? All right. So, and there's the density of sodium metal. Now, this is kind of an interesting question. So first of all, a lot of times in chemistry, we have like chemical reactions, and they're kind of like a recipe, all right? And if you're making cookies at your house, you don't want to add too much flour or too little flour or too much sugar or not enough sugar, et cetera, et cetera. I would say chocolate chips, but I would think you can always have more chocolate chips. But anyway, I digress. My weakness for chocolate chips. Profit back on, which means I'm babbling. Anyway, in this experiment, we need 0.125 moles of sodium metal, and we wish to cut out a cube of sodium. Okay, no problem. So what we're going to do here is we're going to take the moles of sodium and see how that translates into a volume of sodium. And that's where this number is going to come in, the density. We can go moles to grams of sodium using the molar mass of sodium on the periodic table. And once we have grams, we can then use the density there to find the volume in centimeters cubed of our cube. And then assuming that it's a perfect cube, volume equals side cubed. So the cube, like a Rubik's Cube or something like that, length, width, and height are all the same. The side to the third power is equal to the volume. If you have the volume and you want to find just the length of the side, all right, what you can do is do a cubed root. And on your calculator, if you're fortunate to have a little square root with a 3 above it, that's called a cubed root. The number 2, if you cube it, so like 2 times 2 times 2 is the same as 2 to the third, that equals 8. A cubed root of 8 would be equal to 2. It's like going backwards to the most recent thing. If you have this on your calculator, you are good to go. If you don't have it though, you can also do this. You can also put in parentheses whatever volume you use and raise it. That's a caret, raised to the power of 1/3 in parentheses. That's another way to do a cubed root if you don't have that that cool little cube root symbol, and that's totally fine. So there's multiple ways to do these kind of questions. All right, so let's do some math. We're going to start with the moles. We're going to use the molar mass of sodium to go from moles to grams. Sodium is roughly 23 grams per mole. You can get a better value from the periodic table. And once we have the grams, we'll then use the density to turn it into a centimeters cube. So in this problem, the molar mass I used for sodium was 22.99 grams per mole. That's fine. So you can see there how the moles of sodium cancel, and you've got grams of sodium by itself. Now, density is just another conversion unit. So here I'm essentially dividing by the density. You can see I've got 1 centimeter cubed on the top and 0.971 grams of sodium on the bottom. The grams of sodium on the top and the bottom cancel. So in your calculator, you would go 0.125 times 22.99 divide 0.971, and that comes out to 3 sig figs, 2.96 centimeters cubed. Again, I'm rounding up because after that third sig fig, that's a 9. That's between 5 and 9, so we'll make the 5 a 6, 2.96 centimeters cubed. That's the volume of the cube. That's the little V thing I was writing up here. Now, to get to the length of one of the sides, if you have the little cubed root symbol on your calculator, use that here, or you can take that volume and raise it to the 1/3 power. That's a caret, like a little arrow without the bottom stem of it, if you will. It's on there, and you can raise that to the 1/3 power. If you've done that right, it comes out to be 1.44 centimeters. All right, this is the caret right here, caret to the 1/3 power. That's another way to do a cube root if you want to. So if we would cut a cube of 1.44 centimeters length, width, and height, that would give you the volume of 2.96 centimeters cubed, and that translates to the 0.125 moles of sodium that we need. Make sure you know how to do this problem. All right, every calculator is a little bit different. Once in a while, we'll go from a cubed number, like 2.96, back to like this edge of the length of one side, the 1.44 number. And make sure you know how to do this in your calculator. Okay, so that's it for Chemistry 221 problem set number 2. If you have questions on this material, there's lots of resources out there to help you. I have study guides and concept guides in the companion and online. There's also the online-only chapter guides, which have information, and you can talk to the AVID/LSC Center above the library. They can help you out as well. And of course, you can reach out to me as well. I'm your instructor, so of course I can help you out. Cool. I hope this has been helpful. Thank you for spending your time with me, and have a wonderful day.